Welcome. In this video we will use the power factor to examine how the power factor of a load affects voltages and currents in a simple circuit. The simple circuit that we have is up here on the screen, and it actually has a somewhat useful interpretation. If I think of everything to the left of these two terminals that I've just drawn as a utility company that's supplying power to my load, and then I think of my load as my load that is drawing power from the utility company, we can get an understanding of why utility companies like loads with power factors that are close to 1. This 0.2 resistor models, or 0.2 ohm resistor, models the resistance that you would see in the wire that a power company uses to get the energy from wherever it generates the power to wherever you use it. So what we're going to look at, in fact, is the power dissipated in this 0.2 ohm resistor as a function of the power factor of this load. Okay. Now, the information that will be given is one, that the load, the magnitude of the voltage for the load is going to be 170 volts. This is peak value. Okay. And this corresponds to an average or an effective value, RMS value, of 120 volts. Okay. We're also going to be told that the actual power, the actual average power of our load, we want to be 5 kilowatts. So the power company needs to deliver 5 kilowatts on average to my load here. And we'll use the definition of the average power, which is that it's 1/2 times the peak to peak, or the peak voltage on the, or the peak voltage times the peak current times the cosine of theta minus phi, where theta is the phase angle of the voltage and phi is the phase angle of the current. So basically this is the cosine of the difference in phases between the voltage and the current. And this whole cosine of the phase differences is the power factor, which we denote as PF. Okay, so another way of writing this would be 1/2 VL IL PF. And we'll use this expression to solve for currents that our load will require for different power factors, and then we'll use that current to determine how much power would be dissipated in the 0.2 ohm resistor. Okay, so let's start by assuming that we have a power factor of 1. Sometimes authors will get fancy and call this a power factor of unity. Sounds sort of like there's some karma involved there. And it turns out power factors of 1 are the best kinds of power factors to have. Okay, so if I assume I have a power factor of 1, my load is going to require 5 kilowatts of power be delivered to it. That's P. And this will be 1/2 times 170 volts. That's my magnitude of my voltage, times IL, which I don't know yet, times a power factor of unity. I can solve this for IL. I get IL is 5 kilowatts over 1/2 times 170 volts. Okay, and if I work this out, you have to remember 5 kilowatts is 5,000 watts. I've seen students mess that up quite a bit. So you've got 5,000 divided by 1/2 times 170, and if I've worked this out correctly, This is 58.8 amps. Okay, so that says with a power factor of 1, I need to have 58.8 amps flowing through my load with a voltage across it of 170 volts to get my 5 kilowatts. Okay, if I have 58.8 amps, this is again as a peak value, flowing through my 0.2 ohm resistor, then the power in the 0.2 ohm resistor, this is the power that's dissipated by the line that the power company uses to get the power to you, would be 1/2 IL squared times 0.2 ohms. Okay, IL again is the peak volt or the peak current, and because this is the peak current in a sinusoid, the average power is given by 1/2 IL squared times the resistance, which is in this case 345.7 watts. Okay, so we'll power factor of 1. The power in our 0.2 ohm resistor is 345.7 watts. Okay, so far so good. Let's see what happens if we have a power factor of 0.7. Okay, so with a power factor of 0.7, again, I need 5,000 kilowatts. Or I'm sorry, 5 kilowatts. 5,000 kilowatts would be a lot of watts. 5 kilowatts delivered to my load, and this will be 1/2 times the peak voltage times the peak current times the power factor, which in this case is 0.7. The peak voltage here is 170 again. So I can say then that the peak current is going to be 5 kilowatts over 1/2 times 170 times 0.7. And this works out to be 84.0 amps. So you can see that if my power factor is less than 1, it takes a higher peak current to get the same average power to the load. This, from the point of view of the utility company, is bad. If we look at the power dissipated in the 0.2 ohm resistor, this is going to be 1/2 times the peak current squared times 0.2 ohms. And for those of you that are wondering where this expression comes from, it just occurs to me we haven't really derived it in any of the videos, so I'll come back and show you why that's the case once we've done this example. And when I compute this, I get 705.6 watts. So with a power factor of 0.7, our power in the 2 ohm resistor is 705.6 watts. It's almost double what our power is for a power factor of 1. So again, if you think about it, if you're the power company and your job is to deliver 5,000 watts to the load, you have to generate more electricity with a power factor of 0.7 than you do with a power factor of 1, because some of your power is going to be lost, or more of your power is going to be lost in transmission. So this is why utility companies really like to have power factors close to 1. Okay, so one thing that I just assumed was clear, and I probably ought to make sure it actually is clear, that the average power in this 0.2 ohm resistor is given by this expression. So let's clear that up to make sure. So let's think about, in fact, we can generalize this to an arbitrary resistor. So the power in a resistor is going to be 1/2 times the peak voltage across it times the peak current through it times the power factor of the resistor. Okay, so in this particular case, we're talking about a power factor of a resistor and not the power factor of the load. We've already considered the power factor of the load. Okay, the power factor of a resistor is always 1. Okay, because in a resistor the voltage across it and the current through it are always in phase. That's one of the nice things about resistors. And so if the voltage and current are in phase, the phase difference between them is 0. The power factor is the cosine of that phase difference, which is 1. Now, we can also apply Ohm's law and say that the peak voltage is going to be the current times the resistance. And so if we plug this in now, we get P is 1/2 IL times the power factor of 1, so we'll just ignore it. So it's 1/2 IL squared R, which is this expression that we used twice in solving this problem. Okay, this is almost the same as the power in a resistor when you're looking at DC circuits, except we have this factor of 1/2. The factor of 1/2 compensates for the fact that the I sub L we're talking about is the peak value of the current. And when we square, and the current is sinusoidal. So the current goes from IL to minus IL to plus IL and so on. When we square that current and find the average, we get half of the peak value. So that's where that comes from. We can use a similar approach to say that the peak power is 1/2 times, or I'm sorry, the average power is 1/2 times the peak voltage squared over the resistance. So again, it looks like the power relationships you're used to from DC circuits, but you've got this 1/2 here. And in another video, we'll talk about the idea of effective or RMS voltage that's been defined in such a way that you don't have to worry about the halves. So that concludes this video.